I remember the home tasks. Do you remember? So let us concentrate on the Schouten condition. So the task is to demonstrate that the equation I have written describing the compatibility condition is equivalent to the Schouten bracket. So the sum over S P okay, 1 I D P S J K dx S cyclic permutation and this also cyclic permutation. Equal 0. That this is equivalent to the Schouten bracket. So let me remind that x, y, the commutator of vector fields, is a vector field x d over dxi so we remember these are coordinates on our manifold, and these are coordinates on vector fields, so the component of vector fields. So this is a vector field such that its ith component is let me write it. It's more invariant definition first of all, y L y x, and it means that x y I I'm sorry I is so what we have to do, we have to differentiate the coefficient of the vector field y with the vector field like this. So it means that it is the sum over j x j d y I over dxj and minus y j dxi over dxj. So there are big x and small x. X, these are coordinates on our manifold, on our space, and big X are a component of the vector field. So this is the commutator of vector field, and we can expand this operation to polyvector fields by the Leibniz rule. So if, for example, we have a polyvector field like this, we can calculate its Schouten bracket just by the Leibniz rule, x z y plus x y z, and we will use this formula for decomposable bivectors just by induction. And now we have a pi as pi I j d over dxi over dxj. And we can interpret it as the sum of ij Okay, just for like this, and these are two vector fields. So we have to calculate the Schouten bracket between them just component-wise. We have to demonstrate that this condition is equivalent 1 is equivalent to pi 0. This is the task.
So we need to calculate this thing, right?
Yes, we have to interpret this as a vector field x, this as a vector field y.
Like this?
Yes.
Put everything there and...
Yes, and to calculate the Poisson bracket between such decomposable bivector and another one. So how to say, I don't know, the sum xij, yij.
Okay, so...
I'm sorry, ij.
So I write it to be like this sum of ij is x3 xi So this whole thing is, how can I interpret this one?
You calculate the bracket, it's
Which bracket?
the
Oh, this bracket.
Yes, of course.
So you can use this bracket to express this one.
So you see xij is equal pi ij d or dxi. Just like this.
Yes.
You see here we have a summation, yeah, but here
We have summations.
no, here it's just one component.
Okay, so I think we can find it. We can find it from here. Right, so if I write compactly, it will be for now ij is xij, right? But ij something like that.
What is this?
This pi.
No, it
Pi
is already here.
Yes. Like this.
Oh, yes, just like this. And let us. I'm sorry. We need the following: pi 1 and pi 2. Okay.
Okay, and so.
So in fact, the most simple calculation is with 1 pi. So maybe it's the good thing to make firstly this calculation. Just with 1 bivector.
And now we need to show that it somehow goes to 0, right? It will be 0.
Yes, we have to show that it is equivalent to this condition.
So, but how can I find here definition of these pi's? So what is my x?
Could you write this expression? What should it be equal to?
Well, it will be some xz. And this w. And there should be some y also.
with the wedge product. Mm-hmm.
And then x with this. So we have like x. Let's see. Plus x.
Yeah, yeah. And now, in place of x, y, z, and w, we have to put xij, yij, xkl, ykl. You understand?
Yes.
That's all.
So let's put here. So better to start from here again.
Mm-hmm. Mm-hmm. That's with the wedge product. XKL.
Now, so this commutator between x ij x kl should be some delta, conquer delta. Write it explicitly.
Mm-hmm.
Mistake. Then seems like to be 0.
Yes. And what is 0?
So it will give us some conquer delta.
Mm-mm. No, please see, it's not. No, x is like this.
X is this.
It's not real.
Maybe you need to write explicitly.
Do you see some trivial terms in this expression?
Do I see some trivial terms?
Yes.
So if so it will be like xi, commutator between xi and this xk, yes, something like that. And then it will be, it will give us, so this term will appear here, the commutator between these guys, right? And
No. This is 0.
this term.
No.
Yeah.
This is 0.
Yes. So this should be 0, don't we?
No, this is not 0.
Well, let me better write it explicitly.
This is 0, because it's a commutator of constant vector fields. This is 0. Do you understand?
xi, and then I, kl, x let me just look at in one term so that other will be make sense. How can I take the derivative of this?
By the definition? So here is the definition of the commutator of vector fields.
Okay, yes. So it will give us this guy. It will be not 0, it will be something else. Not trivial maybe.
Absolutely not trivial.
Yes, so so then maybe I can directly write it from here by definition. So it will be the sum of xk what is the summation index? Our summation goes over j and k. Am I correct? Wait, yes.
I think you don't understand notation. Let me. Yeah, you see, our vector field is xy pi ij d over dxi. There is no summation here. Okay. But all vector fields are represented as a sum of
this kind of
yes. So it means that xij has coordinates. It has only one coordinate. I is pi ij. So this is a vector field. This is the eth coordinate of the vector field. And this coordinate is equal to this coefficient.
Okay.
And now you have to differentiate.
Yes, so instead of writing this, you need to write this pi.
Yes. Yeah.
So in that case, it should be like our pi ij again pi, but the index will be like kl, right?
Yeah.
Over,
Upper indices.
kl
Mm-hmm.
over ij.
No, dxi. Yes, there is some cognitive conflict.
So you're saying it should be like dxi?
Yes.
That's it?
That's it.
And no sum? And sum goes over I?
Yes, over I.
Now in this case.
But you see, the sum over I is here.
Yes, actually, because it also contains I.
So here we have no summation.
So it's the overall sum that goes over all terms.
Mm-hmm. Mm-hmm.
Now in this case, it will be again pi. What we have here, this vector field y. I should say that this will be again pi ij index. So it will not make any difference because of this x and y.
Could you write the coordinate of ij? What is the k coordinate of this vector field?
Just can write like pi ij. No, the same analogy that.
No, this is this vector field.
So we have used the same thing, and it will be, this will be like some pi.
No.
Just because it doesn't have any pi
No.
here.
There are too many indices, but so what you have to understand clearly that all vector fields on our manifold, the small x are coordinate on the manifold. All vector fields have such representations. Okay?
Okay.
Now our vector field is this one, just this one vector field. What are its coordinates? So these
like
are
one seems
coordinates.
like- So you see that it doesn't have that term, right? So
It has, but very special. Okay, I will write to you. K is delta ik.
Okay.
There's only one coefficient, one.
Yeah, I understand. Yes, the index. Yes, makes sense.
Maybe J. Maybe J. But you see, there will not be differentiation of this, so they are constants. The coefficients of y are constants.
Yes. So in that case, it will be just so it will not 0.
Mm.
Okay. So
Maybe here it also better to write delta ki.
okay. So we write this term. No. There will be just only this Python, right? That's
Yes, yes.
the thing that I wrote before. This pi ij. That is.
So you have written this term now, yes?
Yes, writing on this term now.
So now we have to write the commutator in this definition, but using the coordinates of the vector field to x and y.
Yes, so no minus, because this will not appear here.
No.
And so minus y, this is just this delta, right? I'm right?
X I J. Just a moment. X. You have to write the key coordinate of this.
Yeah, which is the pi ij.
Yes.
And then
And differentiate. And differentiate.
of the Kronecker delta.
Yes. But all these coefficients are 0. So
Then this term will be finished.
Yes.
There will be no this term.
Uh-huh.
We are left with this. And its index will be this KL, right?
KL.
Or this XI, right?
Yes, something like this.
I'm mixed up with the index.
No, it couldn't be so such. Very strange. No, you differentiate this coefficient with the help of this coordinate, not KL, IJ, I think.
J.
L.
Okay, yes. Now it's done. Plus. Now we have this term.
And here else there is some.
There should be L right here.
So you apply this vector field to this. We differentiate this along this vector field, KL, and it is delta KL, I suppose. No, KL, L.
Okay. And now we have the same thing but with opposite indices. Here. Yeah, but here we should like do with yx.
It is certainly more convenient to write it just in coordinates. So you have to calculate, for example, pi ij d over dxi with what? With d over dxl. So this is y kl. And this is x ij.
Yeah, we have already done it.
It is more visible here. It is you have here more chances to make mistake.
Okay.
This is clear. What is the commutator of such vector?
Well, we just explicitly write. So the first term will be.
We just differentiate
0
this along
this.
Yes. Yeah.
Something like this. So what it will be?
No, it will be like this.
Oh, yes, exactly.
That's all. That's all. This is the vector field, which is the commutator.
And so what we have? We have just this differentiation will be how I can write it by dxl.
Yes. Multiplied by the differential, by the vector field.
Yes. We have the same thing. Yes.
As you like. For me, this is
I
more.
think, yes,
more
that's what I've
transparent,
tried to write
yeah.
explicitly everything. So, okay. Then let me write this term with y's xkl. Right. So what is this?
Mm-hmm.
This is just
xj.
I think it's with a minus sign. Because
here.
no, like there is. Yeah, because it's.
Here and here.
Yeah.
Mm-hmm. Thank you.
So this times this pi pi kl divided by xt. So what is this? This is just the derivative of this thing. So it will give us kl j times xk. Is it so?
Mm-hmm.
Okay, so maybe I can erase something and write the final.
Yes, you can erase them.
Maybe you should write yij in the formula.
Sure.
Is ddxj.
No, I'm just writing. I mean, this term, rewriting this term.
Yeah.
Okay. maybe I could write it's okay.
Yes, it's
And now
it's
what
very
I-
similar to
yes,
what
now
we need.
What to do?
yes, but you have to rewrite all these elements in an explicit form.
Yes. Maybe I can write it here directly.
Mhm.
Save some space. So it will be like it was Yij. So Yij is just like this.
And I don't like this. This is not a vector field, it's a function. So you see normally you have an expression of this type.
Yeah, but we have okay.
You,
But we initially wrote it like that. So,
you missed somewhere.
let me then redo this thing. So not to mistake and write everything else. Right. So change. Right.
Yep.
So there will be like two terms. So the first one will be Ij. Nothing to do here. Just keep it like that.
Mm-hmm. Yes, but you see you have the vector field part.
Yes, yes. Maybe better I should remove all these things and write everything correctly. Sorry for that. Okay, so we have Yij, so we have like this. Okay. And then we have that term. And it was so it was EX. And this was right? I. So this image Ij. This was last one. this term is 0.
Okay, okay. So it is similar to what we need. Do you remember what we need?
Do you mean this? So we need to show that somehow goes to 0, right?
No, that this condition that this is 0 is equivalent to this condition.
Yes, and that is what we need to prove, right?
Yeah.
Yeah, so maybe we could look for some Jacobi identity or something like that.
Some what?
Jacobi identity?
No, it is already Jacobi identity.
So something will cancel out, or maybe everything?
First of all, we have to notice that it is a free vector field.
I forgot what was free vector field means.
It has 3 vector field components.
3.
3.
Okay.
Not a bivector, it is a trivector.
Trivector, okay.
Trivector. You see? This, and this.
Okay.
Okay? So we have to understand what are the coordinates of this trivector field. We have to choose the same basis. Yeah, you see, for example, here we have indices j, k, l, but in this term we have indices j, I, l.
So we need to fix one?
Yes, and to combine all the coefficients at the same basis trivector.
Okay, and then what will happen?
We will ask that all the coefficients would be 0. All the coefficients of this
so you
trivector.
mean we should take...
So here we have the summation I, j, k, l.
Yes.
Okay.
Yes.
But this trivector has coordinates at j, k, and l. Yes, d over dx j, d over dx k, d over dx l. And there is some coefficient.
This thing.
Yes. So in sum, we will have an expression. This I, j, k, d over dx I, d over dx j, d over dx k.
Yeah, we'll have some kind of thing, yes.
And this should mean that these coefficients are 0.
0.
But now we have different bases, different notations. For example, this product is expressed in one set of indices, and this product in terms of other. So we have firstly to
let's choose this.
yes. For example, here we have to choose I to k. I to k.
Maybe I choose like this.
As you like. J, K, L.
Mm-hmm.
Okay? But here you have d over dxi.
Okay. So
The simplest way is to exchange k and I in this expression. Do you understand? Principle.
I and K are domains, I think.
Is it clear?
So you will change k to m only
Yes,
here.
only here.
Okay. So this
This is unchanged. This is unchanged by here. So we prefer indices j, k, and l. Is it okay here? No. J, K, L. L is okay, but I is also should be changed to K. Okay? Here,
is
the same. I, J, K, L. K, L we have, but here we have I, so here we have to exchange I with J.
Okay.
Okay? The idea is very simple.
Times the thing that is inside, right?
Mm-hmm.
k should be I, right?
Yes.
So IL, IJ,
No. KJ.
both sides. It should be I.
Yeah.
Oh, there's another term here.
No.
But what to do with this one? Because you take here.
It is already
No,
present.
first you do
Yes. Yes.
Here.
Yes. Yes. Yes.
Okay, now here we have L, so we have J, we have I, and there are two I's, so here I goes to K, so we have again this term, so maybe I can write like this. Okay.
I'm sorry. It is very strange that you have 2I. It is 0 always. There is a mistake.
Mistake.
Yes.
So what is this term? This is the second term, and second term is this one. So this is Yij, and the inside term is here.
Yj. Ij is d over dxj.
Yes, d over dxj
Uh-huh.
times this commutator, and this commutator is what? It's this of Yij times right?
Yes.
So what is
Yes.
in here?
That
The same
Yes.
thing. Times now times this one.
Yes, it is not xi.
Yes, so mistake was with the index.
Uh-huh.
KL.
Yeah.
And here should be
K.
the
K. Uh-huh.
Okay, so we have K. And
Just a moment. And now the index I is not good. You see?
maybe we can.
K and L are good.
Here.
So here we have to exchange I and J.
So we have K and J already,
Yes.
and from here we change I to J. No, I to L.
L. I
should
to
be,
L.
Yes.
Yes. That's better.
Yes. So then, directly right. If I to L, then it will be like J divided by XL, right?
Mm-hmm.
And
Multiplied by pi KL.
wedge pi.
No, it's not wedge. Wedge is between vector fields. We have already
Just multiply, yes.
just multiplication of functions. Yes.
Now plus. We come here. We already have this L. We have K, and then I should be
Uh-huh.
J.
Uh-huh.
So
Yes,
then we
it's
have,
better. Yeah.
then it will have like the same index. It will not change actually. Here.
Very good.
So to make it 0, this whole term somehow should be 0.
Yes.
And if this is 0, and then what? Is there any similarity?
They are equal.
Yes, they are equal, but in the same sign.
No, they are not equal.
Ah.
there is a derivative on different variables.
Yeah, this is over j and this is over I.
Yes, could you say something?
So they are dummy indices.
J. Yes,
So maybe
I.
we can change the differentiation variable.
So there is some strange, another strange. I prefer here to have I. Could you verify?
Let me check. Yes.
Yes. Okay, but if so, these terms coincide, and we have something very strange.
So what we actually want? We want.
It is written, so we want this expression.
So there should be a same summing index, and then all the terms will come up. So let me.
I will write you what we need. You see the sum over S P I S D by J K dxs plus P by J S D by Ki dxs Ks d by ij. Yes.
We already have 4 terms.
Yes, that's strange.
Yeah, but you see how 4 terms comes. From here there should be 2 terms,
Yes, yes.
and from here there should be 1 term, and here 1 term.
And you see, both things are correct. So we have to understand why.
And maybe we can sum these 2 up and write 1. Can I do like that?
Yes, but they will be constant too.
Yes. There will be some-
That's strange. And I don't really like this term. This is all L.
Yeah, you see this
No,
term comes from.
No. This is not correct.
This term comes from here. Yes, here. Here we did what? We
I
changed.
should be L, but L should be I.
It's better. It's better.
Yes.
I
So
and
we changed
here.
only one,
Uh-huh.
and we didn't change
Yes.
the other.
Yes. That's.
So I think
I'd like to make some changes. We have the order JKL. Here it is not the correct order, and our bivector is skew-symmetric. Remember, I'd like to write it by JK and to write here plus.
We'll do
Okay.
the same thing.
And here LJ is okay, but KJ is not. KI. So we always differentiate on the first. So here I also
IK
IK
and
and
plus.
here plus.
Yes. But still you have 4 terms, so
There is another thing to understand, but you have to remember what is the wedge product. It is skew symmetrization, you remember? So if you change indices here, it appears with the same object here, with the same tensor here, skew-symmetric tensor. But here you have to change all indices. So in fact, all these terms should be taken 3 times.
and then something will like
Yes, and
cancel out,
yes,
and then you will end up with
yes,
3 terms.
yes.
Okay.
Yes, but maybe it is also a good thing to think at home alone
Maybe to
with.
check with.
Yes. Thank you very much. We are almost reached. We have almost reached. Yes, of course.
If
we have a symplectic form, we have introduced, we could define a Hamilton vector field as right.
Yes. What?
If we have a symplectic
Yes,
form, we
yes.
could define our Hamiltonian vector field.
Yes.
My
You
question-
mean this is the I?
Yes, yes.
Okay.
And,
Yes, that's right.
If we have now, well, this is not degenerate, but this may degenerate. So,
Yes.
So this, but man is not.
Okay.
Not.
Yes.
But my question is, can we now still define
The Hamiltonian vector field?
yes?
Yes, of course.
So I think it's much more easier to calculate this thing as this, and we could use this to calculate to get result.
It's quite possible. Yes. Do you know what is the equivalent condition to the Schouten bracket of pi in the non-degenerate case for omega?
Non-degenerate.
Yes, in non-degenerate case, a bivector is the same structure as a symplectic structure.
That's it.
Yes, but what is a condition? I will write it. If pi is non-degenerate, then it defines omega, which is pi minus 1. So in this case, these are the same data. They define each other. What is the condition on omega equivalent to pi. Do you understand the question?
You mean they inverse defines by pi compatible with
The question: if pi is non-degenerate, means invertible, it defines some differential form, two form. Omega, which is in coordinate, is just given by inverting the matrix of our bivector. My question is, what is the condition on this form which is equivalent to this condition on the bivector? Do you have ideas?
So you're saying
If pi is such that its Schouten square is 0, what does it mean in terms of omega? Okay, it is equivalent to this condition.
Yes, symplectic form are close to this definition.
Okay, but if we don't know that it is a symplectic form, we have just taken a bivector which satisfies this condition. My statement is that its inverse will be closed. So this is the quadratic equation which we get after turning to the inverse matrix. This is a linear condition. But when we consider its inverse matrix, we get some quadratic condition, which is the Poisson bracket, Jacobi identity of the Poisson bracket. No, it's not so obvious. Yes, we know that if we start from the symplectic form, we get a Poisson bivector, but it is invertible. So these conditions are it is a good home task to demonstrate this. But now we get to, we proceed to the quadratic Poisson structures. Quadratic Poisson structures compatible with the linear one. So I would like to recall you the open to the chain. It is defined by the Lux operator a1 an b1 bn minus 1 bn minus 1 and so its Poisson structure. So you remember that A are just momenta, Bi are some exponential of positions. If I remember, it is like this. So I'm sorry, it's Q positions. So if we start with the standard Poisson bracket in terms of the position in momenta, we get some Poisson bracket between A and B. These are Flaskov coordinates for the open to the chain. It is something like AI, BI is, I don't remember, maybe 1 over 2 BI, like this. So it resembles a lot the SLN Poisson bracket, but we know that this Poisson structure is expressed in terms of the R matrix bracket L1 plus L2. There, the R matrix, if I remember well, is the sum over I less than J Eij Eji minus Eji Eij. Okay. So my statement is that the Poisson structure is compatible with, let me write it 1 here, with L2, which is the same R matrix with L and L. So this is a quadratic Poisson structure. So the do you understand why it is quadratic? What is quadratic?
This L tensor L down here.
Yes.
In the right hand side.
Yes. And what is quadratic?
Now if we complement the bracket between AI and B.
Mm-hmm. Yes, and it will be quadratic. Or in other terms, here in matrix form, we have Poisson bracket between all coordinates on our, all coefficients of the Lux operator. In terms of the coordinate of Lux operator, we get quadratic expression. So the coefficients of the bivector, just pi ij, are now some quadratic expression in terms of L. Okay. So I'd like to comment firstly let's suppose that 2 is indeed a Poisson bracket. bracket. If we suppose this 1 and 2 are compatible, and the argument is the same as in the argument shift method. So let us consider a new coordinate on our space. So we just consider L plus I don't know, identity matrix. So it means that we consider coordinate a I prime, which is a I plus 1, and b I prime are just bi. So it's a very simple change of variables. In terms of such a matrix, the quadratic Poisson bracket has the form R. So it is just the same as the bracket of L with L. It is R L plus L, and this is R L tilde minus ID, L tilde minus ID. And what it is, it's better to place here a parameter lambda, and here delta, and then it is R L tilde minus lambda R L tilde 1 plus L tilde 2 and plus lambda square R ID, but this is 0 because it is an identity matrix. And we get that after this change of variables, our initial Poisson bracket has the form of the linear combination of the quadratic bracket and the linear one. But it is the initial quadratic Poisson bracket. It means it is a Poisson bracket. So it demonstrates that this linear combination is a Poisson bracket for all choices of the parameter lambda. Okay. So now we will try to comment this, but the best way, I think, is to verify it in simple examples. Let us do it for n equal 3. Let us verify that it is a Poisson bracket for n equal 3. Let us start with n equal 2. I will recall you the definition of R. So it is a matrix. It can be represented by a matrix 4 by 4. And it is like this: 1 minus 1. Do you agree? This matrix. So what is now this Poisson bracket. So L for us is A2, B. What are the Poisson bracket between these variables with this quadratic form? We have to write down the right side of this form. Just in coordinate how.
This R is this one. And L is this. And just
Yes, and I have written it in
yeah, matrix form.
already in matrix form. Yeah. Yes, but it is more useful maybe just to write the Poisson bracket. You will see that very simple, quite simple. Yes, but the goal is to verify the Jacobi identity. Okay, I think you could continue it at home. Yeah.
You only have to compute the tensor product and then take the commutator.
Yeah.
That's what you have to do.
Yes. Don't understand how it works. Then, so it's a Poisson bracket for generic n. Some auxiliary question, I'm not sure, but it's quite probable that this R satisfies the classical Yang-Baxter equation. Do you remember what is it? So it's a question, and it is a home task 4. If okay, we finished for today. You have many things to do.
To calculate to verify.
Yeah, sorry.
You mean to calculate to verify it?
Yes. If this R satisfies the classical Yang-Baxter equation. So there is some general statement that if this matrix satisfies the classical Yang-Baxter equation, then this formula is a well-defined Poisson structure.